Yeah, so we're starting to talk about energy storage. We have to all get on the same page as how we're measuring energy. And I'm going to use a kilowatt hour as my unit of energy. And what represents a kilowatt hour of energy? Well, if you use a toaster, which uses a kilowatt for an hour, you'll use a kilowatt hour of energy. It takes a kilowatt hour to raise a metric ton of water or rock 360 meters high. You need to extract a kilowatt hour of energy from water to freeze it, to freeze 10 kilograms of water. And if you want to heat 10 kilograms of bricks to 425 degrees C, it will take a kilowatt hour of energy to do that. 7 meters per second wind passing through 4 meters squared area for an hour generates a kilowatt hour of energy. Sunlight striking 4 meters squared at the Earth's surface for an hour, assuming 25% efficient solar cells, can also generate a kilowatt hour. It takes about a kilowatt hour to drive 5 kilometers in a typical car, and 100 mils of gasoline can supply a kilowatt hour. Gasoline is very energy dense, 10 kilowatt hours per liter. 260 liters of hydrogen at standard temperature and pressure, if it's burned, will generate a kilowatt hour. So hydrogen needs to be substantially compressed to be able to store energy in any reasonable way. And 2 liters of charged lithium-ion batteries can store a kilowatt hour. So I want you to remember these numbers. World energy use from all sources, and this is 2019 data, is about 160,000 terawatt hours. So this is everything. Fossil fuel use, electricity for transportation, burning wood for heat, and so on, everything. And world power use is about 20 terawatts. So a terawatt hour, a tera means a trillion, which is 1,000 billion. So a terawatt hour is 1 trillion watt hours. It's 1 billion kilowatt hours, and it's about the average daily electricity use in California, 0.7 terawatt hours. And a terawatt is 1 billion horsepower, roughly. So these are big numbers. And if you take a look in 2019 data at the energy use in the world, fossil fuels, coal, oil, and gas make up about 3/4 of total energy use in 2019. The renewables are up here at the top, very small. So for me, this is a bit of a depressing graph because it shows the magnitude of what we're facing. We have to eliminate 130,000 terawatt hours of fossil fuels, and we have to hope it doesn't get bigger. You know, oil is an upward slope and gas has an upward slope, but thankfully coal looks like it's leveling off. So this is our goal. We have to get rid of all this fossil fuel use. And fortunately, solar and wind are cheap and abundant, and they're being installed rapidly around the world. But the problem is the sun doesn't always shine and the wind doesn't always blow. So we need energy storage big time. And I want to talk about at first what the sensible options that we have are. So probably the best way to store energy is with pumped hydro storage. It's very simple. You have a low-level lake or reservoir, and renewables are abundant. You pump water uphill, and when they're not abundant, you run this water back down the hill through a generator and generate electricity. This is a picture of a facility in Pennsylvania, but the biggest one in the world is in a place called Bath County in Virginia. It can store 30 gigawatt hours, and it can discharge in 24 hours. So it can provide a little bit over a gigawatt. It's actually perfect for my province because my province uses 20 gigawatt hours every day. So this, if we had this system in my province, we could store enough electricity for the whole province for one day. It would be awesome. And these things are pretty efficient, about 70 to 80% round trip efficiency. And the cost is the lowest of any energy storage system when you levelize the cost over the lifetime of the facility. Bath County is over 50 years old and still operating just fine. The problem is that the amount of water you need to move is enormous. The upper reservoir is 265 acres. The water level changes by 110 feet between charge and discharge, and the head height is 380 meters between the bottom and the top. So there's not a ton of sites like this in the world, but every single one should be developed. And if you want to think back, why are these pumped hydro stations so huge? Why is there so much water? Because you have to elevate a ton of water a height of 360 meters to store only 1 kilowatt hour. So this 30 gigawatt hours represents a massive, massive amount of water. So there's a company called Energy Vault, which instead of doing pumped hydro storage, they are proposing gravitational storage. And the idea is you take 40-ton blocks, you can see some here, and you raise them 80 meters in height. And then when they fall, the cables that lifted them up run in reverse and turn a generator and generate electricity. So you have to ask, how much energy could you store in one 40-ton weight raised 80 meters? So everybody's taken physics in either high school or first-year physics, and the potential energy is the mass times gravitational acceleration times the height. And you can work this out, and you learn raising one 40-ton weight only stores 9 kilowatt hours of energy. And 45 kilograms of lithium-ion batteries can store 9 kilowatt hours. So, this seems pretty dumb to me. And this is what I'm going to do in the first part of the lecture, is talk about different energy storage schemes and group them into the dumb and the good. But nevertheless, this company, Energy Vault, has started to install a big facility in Rudong, China. This is a picture of it under construction. This is a picture of it a little bit later. And the weights go up and down in the middle of this grid structure that you see. But this thing is massive and can only store 100 megawatt hours. Another interesting way to store energy is in heat storage. And there's something called electric thermal storage. 20,000 people in my province have this. And I have an electric thermal storage unit in my house. It's very simple. It's a box of bricks with a bunch of heating elements in the bricks. The heating elements look almost exactly like what you would see in the bottom of your oven. When you turn the oven to bake, this heating element glows red. So these heating elements are energized when renewables are abundant and you heat the bricks. And it's in an insulated box so that heat does not leak away. And then when you want to extract that heat, you blow air through the brick stack and you heat your home or your basement or whatever the case may be. So it's really simple because you're storing heat as heat. You're storing it in the form you're going to use it. And this is really well suited to locations where wind or solar are providing majority of renewable electricity. So does this make sense or not? So how much energy could we store by heating 1,000 kilograms of bricks to 425 degrees C? Well, the amount of energy that you need is given by the specific heat times the mass times the temperature change. The specific heat of brick is about 1,000 joules per kilogram C, and you do the calculation and convert to kilowatt hours. You learn 1,000 kilograms of bricks heated to 425 degrees C can store 110 kilowatt hours. And 1,000 kilograms of lithium-ion batteries can store 200 kilowatt hours. So this is a good way to store energy because bricks are incredibly cheap. and heating elements are cheap. So this is a good way to store energy. And actually, is our estimate reliable? If you go to the website of the supplier of my electric thermal storage unit, you learn that my unit can store 120 kilowatt hours and it weighs 1,000 kilograms, but basically matches our estimate for 1,000 kilograms, just spot on. There's a company in Scandinavia called Polar Night Energy that's making these thermal storage units on a large scale. So what they see is during the summer, when the sun is shining or the wind is blowing, you're using some of that electricity to run your town, but another portion of it is used to heat a giant container of sand. And this thing gets heated and heated all summer long. And then in the wintertime, when it's time to heat your homes, you pass hot water through this pile of sand and run it to the homes and supply heating. And these things can be made as huge as imaginable. And I think it's a pretty good way to store energy. And of course, the reason you would do it this way is because it's cheap. If you're going to use the energy as heat, store it as heat. And now you want to do the reverse, because in a lot of locations, and probably Georgia as well, you know, air conditioning represents a huge amount of electricity use. In Qatar, 60 to 70% of Qatar's total electricity is air conditioning. So we need the equivalent of heat storage. We need cold storage so that solar and wind can freeze a phase change material to deliver cooling when the sun is not shining or the wind is not blowing. You know, so storing cold as cold limits the need for electrical energy storage in batteries. So there's this cool company called Nostromo Ice Brick, and they're in Israel. And they built this device that stores cold as cold. So what they have is a container that has hollow plastic discs filled with water. So each of these little discs is full of water, and you pass heat exchange fluid through this stack of these discs. So when the sun is shining or the wind is blowing, you want to store cold, you run cool heat exchanger fluid here and freeze the water. And then when you want to cool your room or your house when there's no sun or wind available, you run that heat exchanger fluid back through here. And as the ice in the discs melts, it will deliver cooling to the heat exchange fluid and cool your home. So does this thing make sense? Well, the thing is pretty big. It's 14 feet by 20 inches by 10 feet, so it's a long rectangular thing. And it can store about 12.5 kilowatt hours of energy by freezing water. Well, if you do the calculation, this 780 kilograms of water should be able to extract 72 kilowatt hours of heat when it melts. And this thing is only doing 12.5. So it's not operating at its full efficiency. I'm not exactly sure. I think it can be improved, and I think this is also a good idea. And just for perspective, 780 kilograms of lithium-ion batteries could store 150 kilowatt hours. So this theoretical 72 is about half, and this thing is much more simple than a lithium-ion battery, much less expensive. So again, makes sense. Let's talk about hydrogen for a minute. So you're going to use hydrogen to store energy. So you have a windmill. You have to create hydrogen. So you use electrolysis from water, somewhere around 70% efficient. Then you compress that hydrogen so you can store it in some reasonable volume, 90% efficient. Then you have to decide how you're going to use it. If you're going to burn it for heat, That's one thing, but if you want to make electricity, the best way is with a fuel cell. At the peak power point, these things at best are like 55% efficient. If you multiply these numbers together, 34% efficient. By contrast, if you use a lithium-ion battery, charger's 95% efficient, the battery itself is 95% efficient, you get 90% efficiency. So using a hydrogen fuel cell combination compared to a lithium-ion battery for electrical energy storage means you have to build 3 times as many windmills, 3 times as many solar farms, and so on. Now, if you have excess solar and excess wind, and you're just going to waste that electricity, by all means, make hydrogen and then use it for something later on. But this is one thing you have to bear in mind, is that the hydrogen path has efficiency problems. So lithium-ion batteries are the most commonly used energy storage method. And this is a picture of the Moss Landing Energy Storage Facility in California. So each container that you see can store about 3 megawatt hours of electricity. And this total facility could store about 3 gigawatt hours of electricity. But recently, about a third of it burned down when a section with cells from LG just burned up. And these were all housed in a large building. And that was not a good idea, because it didn't look like this, open to the atmosphere. It's all housed in a building, so that the fire propagated from one container to the other. It was a real mess. And anyway, lithium-ion batteries are by far the most implemented electrical energy storage system today. And I want to talk now in the remainder of my time about lithium-ion batteries. So this is a pretty cool graph that appeared about a year ago with the New York Times. How California powered itself in April 2021. This is from midnight through till noon and back till midnight. It was a typical average day in April. And you can see that solar provides a huge fraction of the electrical energy midday. But in the evening, you have to use a lot of gas and imported power to meet the demand. But California installed a lot of battery storage, including that Moss Landing facility that I showed you. And you can see that in April 2024, batteries provided a huge amount of the electricity in the evening when people come home from work. You can see the amount of natural gas that's needed has been dramatically reduced by about a factor of 2. And also the imports reduced by, a third or so. So this is really an impressive graph. So one question that you should ask is, how long do you want the batteries to last? And if you want them to last a long time, can you be sure of that? So lithium-ion batteries, I think for this audience, most people understand them really well. I'm not going to talk about how they work. In this lecture, I'm going to focus mostly on NMC materials, NMC 532 and 622. And one of the reasons that lithium-ion batteries are used in energy storage is because they have the highest energy density, good for EVs, phones, and tools, things that move around. They have a long lifetime, almost no self-discharge. They come in convenient sizes and shapes. They're affordable, and you can design them to be charged in a very short time. So this figure shows a typical morphology of NMC positive electrode particles. They're typically spherical. And when you zoom in on them more and more, you see these spheres are made up of a whole bunch of primary crystallites that are bonded together at the grain boundaries to make up this sphere. And why are they like this? It turns out that lithium-ion diffusion is pretty fast along the grain boundary. So the lithium ions can go from the electrolyte to the surface of the particle and then into the interior pretty quickly with this type of design. So let's see what happens when we use these type of materials in a lithium-ion cell and operate it for a long period of time. So a typical NMC graphite cell has a voltage which varies with the state of charge, shown here, voltage versus state of charge. And when the voltage is higher, the positive electrode is more reactive to the electrolyte in the cell. So for this reason, a lot of EVs and other devices often restrict the upper cutoff to around 4.1 volts like this. And many researchers and users operate their cells under restricted state of charge ranges. So you might go from 100 to 75%. This would be 25% depth of discharge, or from 100 to 50%, it would be 50% depth of discharge, and so on. And one other thing that you need to know about these NMC materials is that their crystallographic unit cells change as a function of the state of charge. So as lithium is removed from NMC 622, one of the crystallographic axes shrinks and the other one expands. And you'll notice how these volume changes are anisotropic. One is shrinking, the other is expanding. And the problem with this is that you can get microcracking along the grain boundaries of these NMC particles, because the particles are, one of them is expanding in one direction, the other in the other, and they're contacting each other, and it just shears along the grain boundary, and you get this microcracking. So how do we avoid microcracking? So the experiments I'm going to show you are made on small lithium-ion pouch cells. They're made in China and supplied to us without electrolyte, and we fill the electrolyte in our lab. So this gives us control over the electrolyte, which is a very important factor determining battery lifetime. So here's some data that one of our students, Roby Gauthier, collected. So this is showing discharge capacity versus time. Well, cells are being charged and discharged at a 3-hour charge and a 3-hour discharge. And these are NMC 622 graphite cells. The green cells are being cycled between 4.1 and 3 volts, 100% depth of discharge. The red are 75% depth of discharge. The blue are 50, and the black are 25% depth of discharge. So you can see the discharge capacity scales with the depth of discharge range, as you expect. But every roughly 500 hours, in all cells, we do a 100% depth of discharge, so-called checkup cycle. And you can see that when you're cycling over the 25% depth of discharge range, every time you do a checkup cycle, you can see you get way better capacity retention than if you were doing 100% depth of discharge every time. And the same is true for 50 and 75. It's better to do these repeated small depth of discharge cycles as opposed to a lot of 100% depth of discharge cycles. Now, one thing you need to remember is all these cells after 20,000 hours have all passed the same amount of charge in the charge and discharge directions. And doing the small depth of discharge cycles leads to much better capacity retention. And just as a point, if this was used in a 400-kilometer EV, the vehicle would have traveled about 1.5 million kilometers, okay? So even in the green case, it would be fine. But if you're interested in having a lot of battery life remaining, it's better to do a lot of short drives followed by charging. So we wanted to take a look and see what was happening to these cells. So Toby Bond at the Canadian Light Source did X-ray CT on them after cycling for a very long time. And I'm going to show you some pictures at the highest magnification of 340 nanometers per voxel. So this is X-ray CT over on the left of the cell that's brand new. You can see the spherical NMC particles. And after 25% DOD cycling for 2.5 years, the particles look almost the same. But after 100% depth of discharge cycling for 2.5 years, you can see the particles are all cracked into pieces and almost completely destroyed. And this is because the volume changes of the particles are greater when the depth of discharge range is greater and the effect of microcracking gets more severe. And it's amazing that the cells even work at all after these 2.5 years at 100% DOD. So this again really shows you the importance of keeping the state of charge range that you're operating your cell small when you have these spherical NMC particles made of many, many primary particles. So let's just take a look at more data for these cells. So we've tested these cells for up to 7 years so far. And the cells where we're doing the 25% DOD shown in black, it's almost no capacity loss at all. And when we look at the 100% checkup cycles, there's very little loss in energy over the 7 years of continuous operation. Whereas when you're going at 100% DOD, you can see, more accelerated capacity loss. And the difference is much, much greater if the cells are tested at 40 degrees C. Here it's only out to 3 years, and you can see that the cells going 100% DOD are declining pretty fast compared to 25%. If you wanted to know how long this could drive your vehicle, 4 million kilometers at room temperature, 2 million kilometers, and with still lots of battery life left. So it's pretty amazing. This is an article came out about a year ago in the Toronto Globe and Mail. It's our most famous newspaper in Canada. EV batteries are likely to outlive the cars they power. That's what I'm showing you on the previous slide. And what I showed you on the previous slide is what I would call a crappy lithium-ion cell because of this microcracking. And if we want batteries to support vehicle to grid, where they're charging and discharging when the car is parked, we need to have better lithium-ion batteries than the ones I'm showing you. Because you don't want the vehicle owner to think they're going to wear out their battery doing vehicle to grid operation. So vehicle to grid is where when the car is parked, it's tied to a bidirectional charger, and it can be charged when the renewables are abundant, and then at night some fraction of the stored energy is delivered back into the grid. And the utility will pay you for this, for storing energy and delivering it back. So how can we improve the situation? Well, we and others around the world recognize the importance of what are called single crystal positive electrode materials. So these are SEM images. The lower one is for typical NMC after 100 cycles, and you see this microcracking. And these are single crystal materials where every particle of the positive electrode is one crystallite. There are no grain boundaries. And after 100 cycles, there's no microcracking observed at all. So here you won't lose electrical contact to the particles in the middle and have capacity loss. This is a figure from a paper that we wrote doing cross-sectional SEM of the positive electrode of single crystal positive electrode material after 5,300 cycles. When you look at the majority of these particles, there's no cracks at all. This one big one that we follow along has this one massive crack, but the rest of it isn't cracked at all. So these single crystal materials are amazing. And when they're put into lithium-ion cells and operated at 80% depth of discharge or 90% depth of discharge or 100% depth of discharge over 20,000 cycles, 6 years of testing, there's very little capacity loss. And these particular cells would drive a car 8 million kilometers. This would enable vehicle to grid without any issue at all. So these are batteries that won't wear out. And they can be made today. Single crystal positive electrode materials are becoming very popular in China. Lots of lithium-ion cells use them. This is just an example of vehicle to grid where in the sunlight you charge the car, charge your town, and at night you use the energy stored in the car to operate the town, some portion of it. So why do we need vehicle to grid? Well, this is a forecast from Christophe Pelot of Avicen Energy showing in 2030 how lithium-ion batteries will be used. And the majority of the lithium-ion batteries produced will be used in vehicles, and only this tiny little black box will represent lithium-ion batteries dedicated for energy storage. So if you want to bring more solar and wind on the grid and you say, I need battery energy storage, where are you going to get the batteries? All the new battery plants that are being built, especially in the southeast US, they're all targeted for EVs. The output is going to EVs. So you'll want to be able to support vehicle to grid operation. And if the batteries are really good and they outlast the vehicle, well, then you can use them in second use. So here's an example of used EV batteries racked up in California and storing energy. Here's another example from a company called Moment Energy in British Columbia, Canada, that uses used EV batteries for energy storage systems. And Moment Energy's just been awarded a big Department of Energy grant to build a 20 gigawatt hour storage facility in Texas using second use EV batteries. So that's going to be pretty cool. This is an example of used EV batteries at our university in the lab of Lucas Swan. These are 4 different batteries out of crashed electric vehicles. Chevy Bolt, Hyundai Genesis, Tesla Model 3 uses LFP, and a Tesla Model 3 with NCA. All different types of batteries, all at different states of health, all racked up together and storing electrical energy and delivering it back to the grid. So batteries don't need to be the same. Battery management system can handle the situation. So why would you recycle the material in the batteries if it's still good? And this is why we need to have long life batteries, right? One of the reasons. Okay, so I'm going to skip ahead here just to talk a little bit about this. So what we're doing in our lab now is really trying to make lithium-ion batteries last a very, very long time, many decades. And our approach is to measure the properties of cells at elevated temperature, 70 degrees, 85 degrees, and then 55 degrees, 40 degrees, and so on, and take the high temperature data and use it to extrapolate the lifetime at ambient temperature, 25 degrees C. Because already our tests at room temperature are taking 7 years and we're still at 90% capacity. We don't know how long things are going to last. So Claire and Sasha have been working on this project recently, and this particular lithium-ion cell chemistry that we've been working on here is projected to last 70 years at 20 degrees C and 25 years at continuous at 40 degrees C. But we need to be sure. And this is a big part of the effort here in our lab, is to really learn to become confident in our ability to project lifetime on the many, many decade scale. And if you think about it, why am I so obsessed with battery lifetime? Well, ask yourself the following question. You own a lithium-ion or a sodium-ion battery. How long do you want it to last? There's only one sensible answer. as long as possible. So I'm going to give you this little thought experiment here. Imagine if we wanted to be able to store enough energy from solar and wind to power the world for one day in a single charge and discharge of a huge number of batteries. How much energy are we talking about? Well, I showed you at the beginning of the talk that world energy use is 160,000 terawatt hours in a year. So if you say a year has 400 days, to keep the math easy, that's 400 terawatt hours that we use in the world in one day. And let's say that we want to be able to store 400 terawatt hours of energy so that we could power the world for one day in the absence of solar and wind. Well, lithium-ion battery production is 1 terawatt hour per year today. And some projections say it will be 6 terawatt hours in 2030. Okay. So it's a long way from 400. And this is an interesting fact. According to Benchmark Mineral Intelligence, they're a pretty good forecasting firm. It will cost $200 billion to construct the gigafactories to make 6 terawatt hours per year of lithium-ion cells. 200 billion. U.S. military spending in 2023 was $850 billion in 1 year. So what are the priorities here? You know, in the end, if we're going to eliminate fossil fuels, we need to deploy about 400 terawatt hours of rechargeable batteries. If they last 10 years, you need to make 40 terawatt hours every year to replace the ones that are dying. But if they last 50 years, then you only need to make 8 terawatt hours per year in steady state. 8 terawatt hours per year isn't that scary, because in 2030, we're going to be making around 6 terawatt hours per year. Okay. So battery lifetime is really incredibly important, but most researchers don't focus on it because it's hard. It's really hard to make a long lifetime battery and be sure. So I'll just conclude now. The use of fossil fuels has really messed up the earth. We need to stop burning them as quickly as possible. The use of renewable energy sources means that we need energy storage. And I talked about some sensible options. Pumped hydro. Problem is that sites are limited. Heat storage. Store heat as heat when you'll use it as heat. This makes a lot of sense, and it's easy to do. Cold storage. Store cold as cold when you'll use it as cold. This also makes sense. And battery storage, of course, the largest deployed option, also makes sense. Vehicle to grid, to use that all those batteries that are in vehicles to store energy is a really good thing. And to do that without the vehicle owner thinking about, you know, the batteries are going to be worn out, you need long lifetime batteries. And those batteries, even after vehicle to grid, when the car falls apart, you can use them for second life. And basically, the longer batteries last, the better. I mean, it's just simple. And this is a huge challenge to make them last, 50 years and be sure. Okay, so thanks for listening. And if there's any time, I think there's a bit of time left for questions. I'm happy to try to answer them.